Hello everybody. In this presentation, I am going to show you the optimization algorithm used for the maximization of volatile fatty acid production in a dark fermentation process. My name is José de Jesús Colín Robles. I would like to give my special thanks to my advisors, Ixbalan Torres and Víctor Alcaraz. Also, I would like to give my special thanks to the European Control Conference. This is the table of content of this presentation. In the part 1, we are going to talk about the mathematical model of the dark fermentation process. In part 2, we are going to talk about the problem statement and the goal and the optimization algorithm. This optimization algorithm is integrated by these algorithms that are going to be presented in sections 3, 4, and 5. Finally, we are going to talk about the results and conclusions in sections 6 and 7 respectively. The mathematical model used to describe the behavior of the dark fermentation process is presented in System 1. As you can see, this system is integrated by these three states: the biomass, the chemical oxygen demand, and the acetate concentration. This system considers two disturbances: the input chemical oxygen demands and the input acetate concentration. Also, this model considers the control input, the dilution rate. The problem statement is presented in equations 3 and 4. The acetate productivity is modeled or described using the equation 4. This acetate productivity presents an optimum dilution rate for each input chemical oxygen demand concentration, and this optimum dilution rate is considered as a global maximizer. Now we are going to see the productivity of the acetate in this figure. As you can see, in this surface, it is easy to identify a maximum acetate productivity related with an optimum dilution rate for each input chemical oxygen demand concentration. The optimization problem is presented in equation 6. And in this figure, we are going to see the optimization scheme to solve this problem. The Leuenberger observer is working with the supertwisting observer to calculate the input chemical oxygen demand estimation, and this estimation is used by the golden section search algorithm to calculate a maximum acetate productivity. This maximum acetate productivity is used as a reference by the supertwisting controller to generate the control input. With this, we take to the dark fermentation process to its maximum performance in acetate productivity. The golden section search algorithm uses the equation 7 to calculate this maximum acetate productivity. As you can see, this equation is in function of the input chemical oxygen demand and is in function of the dilution rate. In this work, we are considering the input acetate concentration as a constant. This equation was calculated using the equilibrium point of the dark fermentation process. This equilibrium point is presented in equation 8 and equation 9. The optimum dilution rate of this acetate productivity is obtained by solving the equation 11. In this case, the optimization algorithm calculates this optimum dilution rate using the algorithm 3.1. This algorithm 3.1 is the golden section search algorithm. As you can see, this algorithm calculates two inner points of the dilution rate that are function of this natural constant. This natural constant is present in growing patterns, in natural structures like flowers. In this case, this constant is used to calculate these two inner points of the dilution rate. After a few iterations, the golden section search algorithm calculates this maximum acetate productivity and its related optimum dilution rate. On the other hand, the estimation of input chemical oxygen demand is carried out by the supertwisting observer. The supertwisting observer needs the estimation of biomass and chemical oxygen demand at the output of the dark fermentation process. These estimations are calculated by the Leuenberger observer, so they are working together to calculate the input chemical oxygen demand concentration. Now we are going to see the Leuenberger observer equations that are presented in equations 22 and 23. These equations are obtained from a linear approximation of the dark fermentation process. This linear approximation in discrete time is presented in equation 20 and 21. With this approximation, we calculate the Leuenberger observer gains using the H infinity norm. Now we are going to present the supertwisting controller. This algorithm is used for control purposes when the system is under parametric uncertainties and is operating under external disturbance. In this case, the dark fermenter is operating under these conditions. As you can see, the equation of the supertwisting controller are quite simple for implementation purposes. Now we are going to see the results. The simulation test parameters are summarized in this table. The sample time is defined as 5.7 minutes. The operating time of the dark fermentation process is around 1 year. And we added a wide Gaussian noise to the measurements of the acetate productivity at the output of the dark fermentation process. Also, we can see in this table the uncertainties in the parameters of the model. With these conditions, we are trying to approximate the numerical simulations with the real behavior of the dark fermentation process. With this, we can see the results obtained by the optimization algorithm. These results can be seen in these figures. As you can see in this figure above, we can see the input chemical oxygen demand concentration that is used to feed the dark fermentation process. The line in blue are the estimations of these concentrations by the Leuenberger observer coupled with the supertwisting observer. The estimation of the states are the following. As you can see, we have the estimation of biomass, estimation of chemical oxygen demand at the output, and the acetate concentration. Now we are going to see the productivity of acetate in these numerical simulations. As you can see, the red line is the productivity obtained by the dark fermentation process, while the blue line are the reference generated by the golden section search algorithm. In the figure B, we can see the control input generated by the Discrete-Time supertwisting controller, and the blue line are the optimum dilution rate calculated by the golden section search algorithm. As you can see, these results allow us to conclude the following, obtain the following conclusions. The first is that the optimization algorithm is robust under conditions of uncertainties and external disturbances. And numerical simulations show a correct performance even in presence of these parametric uncertainties and in presence of this noise of measurement in the acetate productivity of the dark fermentation process. Also, we can conclude that the optimization scheme presented in this work is attractive for implementation in an FPGA or a microcontroller. And this implementation, the implementation of this algorithm using these technologies allow us to reduce the power consumption in the execution of these algorithms. Then, this is all for this presentation. I am glad to answer your questions. Thank you very much.